we're going to start this discussion with numerical heat transfer. Now, in many systems, the heat transfer can't be solved for analytically. The system is too complicated. Oftentimes, our best alternative is some kind of numerical technique. Now, numerical techniques give approximate solutions to our problem at discrete points. So the solution's not complete and it's not perfect. We basically divide the domain up into many small regions and we solve the heat equation over each region. This allows us to relate all the regions to each other, and we end up with many equations that have to be solved simultaneously in order to obtain a solution. The advantage here is that we can obtain solutions for very complex problems, and it's easy to extend these methods from 2-dimensional to 3D. However, the drawback is one of accuracy. The solutions for these types of problems have some errors associated with the mesh and with the numerical approximations. So we need to make sure we account for those errors when we're talking about our solutions. Now, there are several broad categories of numerical techniques. Finite difference is based on the heat equation, but we approximate the gradient using a linear interpolation. Finite element is also based on the heat equation, but we approximate the gradient with a more complex method. Boundary element methods directly solve the control volume equations by fitting the boundary conditions, but we can only do that for certain kinds of problems. And then the last one is finite volume methods, which are based on the first law. So we get the control volume equation for the first law, and we use a first law analysis to balance the energy in with the energy out. And then when we do that, we have a heat flux. So the heat flux is based on temperature gradient, so we need to approximate those temperature gradients with linear interpolations. Now, finite difference is the simplest method, but finite volume is often the easiest one to understand because we can add up the energy in and energy out from each side of the cell. So that's the one we're going to be looking at over the next couple of slides. Now, the first step in any numerical calculation is to determine your nodal network. Your nodal network is the network of points on which you plan to solve your equation. So then you can sketch a small control volume around each point. The node is the point you're going to be using to solve, and the control volume around that node is your cell. It's important to note that the fluid properties or material properties at a node represent the average properties in the cell. So once you've identified all your nodes and cells, you identify each point with a subscript, an MN subscript, so T11, T12, T13, and so on. Now it's important to note that the selection of these grid points isn't arbitrary. It depends on the geometry of the problem and the quantities you're interested in. It's also important to note that the size of the cells very strongly affects the accuracy of your numerical calculations. Smaller cells mean that the Taylor approximation is closer to the actual derivatives. This increases your accuracy. However, it also means you end up with more cells, so you have more work to do. There's a more computational cost associated with the problem. Now, when we look at these equations, we're going to perform the energy balance for the cell. So we take the heat fluxes in and the heat fluxes out and the energy generation in the cell. So we have energy generation minus the sum of all the heat fluxes is equal to 0. This is the steady state equation. So we're able to neglect the time derivative that would show up on the right-hand side of this equation, and it's just 0. So we have to approximate the heat fluxes with the Taylor approximation. So we have Ka dt dx for the heat rate in. And so we have K, the area is delta y, delta z, and then the gradient is delta t over delta x. So we're going to do an example of this where we have a cell and we're going to derive the finite difference equations. So we start by just looking at the basic equation from the previous slide. And we're going to look at the positive x side. So if we look at the positive x side, which is this side here, this gives us this equation. So we have the thermal conductivity, and then we have the temperature gradient, and then we have the area, which is delta y, delta z. Then we can also look at the x minus side, which is here, the y plus side, which is here, and the y minus side, which is here. So the next thing we're going to do is make an approximation that delta x and delta y are equal. So then we can cancel all these delta x's and delta y's. The next thing we're going to do is, if we look at this, the volume is going to be delta x, delta y, delta z. So we can cancel all the delta z's from this equation as well. And if we add these all together and rearrange the terms, because we also have this right here, so q dot delta x, delta y, delta z, but we've canceled the delta z. So we can rearrange the equation and divide through by k to obtain the equation at the bottom of the screen here. So we have basically all the nodal temperatures around it. We have the temperature of the node itself, and then we have the heat generation term. So we can add 4 times the temperature to both sides, and we come up with an equation that allows us to determine the temperature in that cell. Now it requires that we know the temperatures of all the other cells, so we have to use an iterative solution or some other type of solution technique to solve this particular set of equations.